Hello, and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 100,000 computing professionals and students who are ACM members. I'm Stephen Ibaraki, co-chair of the ACM Practitioners Board, and it's my pleasure to welcome you today. You will find more info on my background in the bio widget on your screen. For those who may be unfamiliar with the ACM or what it has to offer, ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations to sustain competitiveness in a global environment. ACM provides timely computing information published by ACM, including the Communications of the ACM and Q magazines, access to the ACM Digital Library, the world's most comprehensive database of computing literature, and international conferences that draw leading experts on a broad spectrum of computing topics, and support for education and research, including curriculum development, teacher training, the ACM Turing, and ACM Infosys Foundation Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can close or relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during this webinar, please type them into the Q&A box at any time during the webinar and click the Submit button. I'll organize the questions as Mike Hinchey speaks, and he'll reserve time at the end of the presentation to address them. This session is being recorded and will be archived, and you will receive an automatic email notification when it becomes available. And check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you will see a survey open on your screen. Please take a minute to fill it out, as it helps us to improve our webinars. You may also open the survey at any time throughout the presentation from the menu dock at the bottom of the screen. You can also use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACM Learning. We'll be watching your tweets. Today's presentation is Evolving Critical Systems by Mike Hinchey. Mike Hinchey is Director of Lero, the Irish Software Research Center, a national research center based on 8 institutions, including all of Ireland universities. Mike is also a professor of software engineering at the University of Limerick, and at various points, Mike has held full professor or visiting positions in the UK, Germany, Sweden, Japan, Australia, and the US. Prior to joining Lero, Mike was director of NASA's Software Engineering Laboratory and was awarded the 2009 NASA Curley Award as Innovator of the Year. The holder of 26 patents, he is also the author and editor of more than 20 books and 200 papers on various aspects of computer science and software engineering. Now, Mike, without further ado, take it away.
Many thanks, Stephen, and thank you, everybody, for joining us today. I'd like to ask you to think back where we've come from in computer science and how much we've achieved in a fairly short period of time. On your screen right now, you see a photograph of EDSAC. This ran for the first time in 1949, and it was the first computer to execute a stored program. So it was, in fact, the state of the art at that stage. But look at what it was. It was 650 instructions per second, 1,024 17-bit words, paper tape input, and teleprompter output. 3,000 valves occupying a space of 5 meters by 4 meters and needing about 4 times that space around it just for ventilation. It's amazing to think that in 1951, the British government thought they would only ever need 3 of these machines. Whereas if you're watching today on a smartphone or on some similar device, your machine is probably way, way more impressive than that 3 machines. That machine was built in Cambridge, University of Cambridge in England. Another man from Cambridge also had an idea to build a machine many years earlier. Charles Babbage, who you see in the bottom right corner, invented a machine that he called a difference engine because it worked on the principle of partial differences. He only actually built part of it. Some of it you can see in the photograph on the top left. The gentleman standing next to it is Doran Swade, who's about 6'3", 6'4". So it gives you an idea of how big this machine was, even just the part that was built. But many people don't realize why Babbage built this machine. In fact, he built it for a very specific task. What he wanted to do was to fix the problem that errors were being made in logarithmic tables that were used in shipping. And these were resulting in ships being lost at sea, cargo being lost, and lives being lost. So here you can see, for example, a correction made in 1832 that was corrected again in 1833 and corrected again in 1836. Babbage's idea was that if these tables could be computed and ultimately printed in an automated fashion, then this would be a big boost to the shipping industry and reduce the number of errors. He was very lucky to have involved with him this lady, Augusta Ada King. She later became Augusta Ada Lovelace because she was the Countess of Lovelace. And she developed many of the techniques and ideas that we use nowadays in programming. She understood software reuse. She understood the principle of programs. She understood the idea of subroutines and many, many other things that we now take as routine in programming. This is a somewhat old chart. It only shows up to the year 2000 or so, but we can probably imagine that the figures would continue on well past that. If we look at hardware systems, so if we look at computer systems that appeared in the 1950s and they were reasonably reliable, and they got much more reliable over the years. Telephony systems were certainly reliable by the 1950s, and that continued on. But look at the software equivalents of these. Mobile phones being the software equivalent of telephone systems, and the internet being the software equivalent of a computer system. We see that these are actually declining in the 1990s and probably are declining more beyond 2000 as greater demand is put on these systems. So software differs dramatically from hardware, and I know we're preaching to the converted here, but we know that software is everywhere, but we don't necessarily see it. How many people realize that they use hundreds of thousands of lines of software every morning just to get to school or work? It's something that is abstract. We don't see it physically, so therefore we don't necessarily know that it's there. And as a result, we think it's something that's easy to change. And we've all heard the stories of the 15-year-old writing an app in his bedroom and selling it for millions. And everybody thinks we can change our software. It's easy to change it. And because we think it's easy to change, we do it often. But the problem is we don't necessarily do that well. And we don't then necessarily notice that it is deteriorating in quality as we change it. This is a chart that comes from Roger Pressman's book. And what it shows is the idealized curve when we develop software. So when we develop our software, the first version usually has some problems, and we have some things that we need to fix. So ideally, we would fix things over time, and ultimately we would have some problems that we would decide to tolerate because it's just too expensive to repair everything. But in actual fact, what happens, the actual curve that's shown here on the chart, is that as we fix problems, we create other problems, and we have a knock-on effect so that the result is the actual curve that's showing in this chart rather than the idealized curve that we would expect to have. And of course, there's been many examples of software failures. Lero 25 was an example where a number of women were given massive doses of radiation in and around the Seattle area because interlocks that were done originally by hardware were changed to be software, and were overridden by radiographers on a regular basis. Ariane 5 is a famous example where the European Space Agency ported software from the version 4 of the rocket, Ariane 4, and to Ariane 5, and it implemented a routine that was not actually needed. It was needed in Ariane 4 to keep the rocket on the launch pad until it was ready to go, but it wasn't actually needed in Ariane 5, and what it did was pull the rocket off of its correct trajectory. And then, of course, if we tell something about the European Space Agency, we have to be fair and point out problems that NASA had with the Mars Polar Lander, for example, where jitter in the undergear made the lander think that it was actually far from the planet's surface, and therefore it had to speed up in order to get there, whereas in actual fact it was close to the surface and it should have slowed down and reverse thrusted. And of course, there are many, many more examples of these software failures, and there are some excellent books that detail some of these. The problem is that we make things more complex than we need to. The problem is complexity. This is a chart from the April 2009 issue of IEEE Computer, and it shows the number of applications in various areas that are being built every year and the size of these. So you see that airplane navigation is not so many. You see huge numbers of mobile phones and high-end mobile phones, and of course things like pacemakers. From the same article, there's an interesting chart that shows the increase in size in various types of systems. So for example, space flight control, you can imagine, got much more developed in the 1970s and 80s. And the interesting one here is switching systems in the blue squares. The Linux kernel, which is the yellow squares, you can see that increasing dramatically during the 1990s. But probably the surprising one for most people is the green triangles, which is automotive software. So essentially there was no software in cars in the early 1990s, but now most high-end cars have upwards of 70 processors in them, each running software and each talking to each other to do various things. And we're actually in a situation now where some car manufacturers are updating the software on a daily basis. Now in many cases this is the entertainment system, but it's going to be the self-driving car, and it's going to be having software updates and changes on a regular basis. So the problem is that we want more, we expect more from our software and our systems. We have strict constraints on the timing that we will wait for things to happen, and obviously there are certain things that we can tolerate and other things that we won't. So we want to do more things, we want to reduce costs, we want to have more functionality, and we want our systems to change constantly. So, quote from Albert Einstein, any intelligent fool can make things bigger and more complex, but it takes a touch of genius and a lot of courage to move in the opposite direction. So essentially, we want to be able to understand that our software must change, but sometimes we don't want to make it too complicated. So our software isn't static. We have legacy systems that have evolved over periods of time. We've brought together separate subsystems that might have been because of mergers and acquisitions or takeovers. We've had new hardware and software technologies that we want to exploit. So for example, we want to use cloud-based structures and so on. We have new requirements by our users. We have new changes that are needed every year by regulatory bodies. So our software does change over time. But also, and from my own point of view, much more interesting, is software that changes at runtime. And this is because we couldn't necessarily predict everything that would have happened at the outset. The software has to change when new situations are now known, things that we couldn't have completely planned for. And we'll come back to this later. So essentially, software is supposed to change. If it weren't supposed to change, we'd do it as hardware because we're probably better at doing it than hardware. So the big advantage of software is this ability to evolve. We are talking, of course, about critical applications. We're talking about systems where if they fail, they could damage property or destroy property or even kill people. We're also talking about systems where breaches of security cannot be tolerated. But our definition of critical is broader than that. That we don't mean just safety critical and security critical. We also mean essential to an organization for its product base, for its competitiveness, its profitability, etc. So this is now in automotive systems, medical devices, and we can classify financial services in this way. So we have software that's widespread, widely used, and often invisible. We have a lot of legacy code that's being badly structured, badly maintained. We have lots of software failures and declining quality in our software. We have diverse hardware platforms, complex physical environments in which we want the software to operate. We don't have qualified numbers of developers and testers. We read constantly about the shortfall in the number of people being trained in computer science and graduated in computer science. And certainly the techniques that we've built over the last 50 years or so are not doing anything to resolve that problem. So that's why we're proposing this area of evolving critical systems. We're looking at systems that have evolved from legacy code or legacy systems because we combined some component-based systems, possibly over periods of time, as I mentioned, because an organization is evolving in itself. Or we're doing deliberate changes to exploit new technologies, such as I mentioned, cloud. Or we're looking at software that changes as it runs, and it must do this to meet changes in the environment that were not necessarily previously known or previously planned for. So we want to be able to develop complex systems, complex critical applications that are important to our organization, that we can describe in such a way that the developer will fully understand the necessary functionality of the system. So this means we need to do work in the area of requirements engineering. And on the next few slides, you'll see areas of research in italics. We are looking at systems that must be expressed in a clear and precise way, so we need formal specifications. Well, yet we want to offer sufficient flexibility to allow organizations and follow processes and practices that they have defined for themselves, whether that's agile methods, etc. This is an interesting chart that comes from the NASA controller. And I don't know how accurate the details are. Each of the red dots corresponds to a NASA mission. It doesn't really matter what they are. But what this shows is that when NASA invests very little in its requirements, so in the region of 2 to 3%, it can have a cost overrun of about 200%. Having the other end of the scale, when it invests about 15% into requirements, it has a cost overrun of maybe 10%. As I say, I don't know how accurate this is, and I suspect that the curve is up to the right rather than where it's showing on this. But it does show that investment in the early stages makes a huge difference. We want to be able to understand the architecture of the system well. It's going to be the basis for future changes that we make, and it's going to be important that we understand the effect that changes in the architecture will have. And this is really so when we're talking about systems that evolve at runtime, that these are adaptive systems, whether you want to call it autonomic computing, organic computing, self-adaptive systems, or one of these other areas, all of which have ultimately the same goal. And we're going to need models that are going to be a key component for our system, that these models are going to be used to understand the changes over time and give us an understanding of possible difficulties we will have. And we want to use these models, too, for possibly automated code generation, and this is going to be important to us. The system must be structured in a way that change can be controlled and clear. It will have a fixed core functionality, and then other features that can be changed, adapted, swapped in and out in order to support the evolution. So this could be a software product line approach, for example. And we want to make sure that the quality and reliability of the system is not impaired as it evolves. So we want to continually overview the development and the evolutionary process. We're going to have to ensure that policies and constraints are met and applied in relation to the government, to the organization's plans and governance. And we want to collect and record data and evidence to show that we are maintaining the quality and reliability. And we want to compute various measures that will enable us to determine this and to demonstrate this over time. So we've been developing this ECS, or Evolving Critical Systems Research Agenda. The idea is to build software that is highly reliable to begin with and that maintains this reliability as it evolves without incurring prohibitive costs. And in many cases, we actually would hope to improve the reliability as we evolve the software. So we've defined a small process that basically means that we plan, we execute, we assess, and we do this with tooling in the background at all times. This is a little bit of a joke because peat is what makes Irish whiskey taste very good. So, but the process, as we define it, is not terribly different from other processes. So, for example, this is the MAPE process, or the MAPE-K process, as it's sometimes known, defined by IBM in terms of autonomic computing. So you see it does something similar. It does monitoring, analysis, planning, and execution, and there is a knowledge base used around this. So here are some of the things that we do in Lero. I'm just going to mention them very, very quickly. So we were working in the area of smarter cities. One of my colleagues is particularly focused on traffic management and looking at ways that traffic can be diverted because of problems, traffic jams, burst pipes, special events, etc. We're working in the area of software product lines, and we have a substantial group in this area. And one of the things we did was to help an industrial company, whose name I cannot mention, but a company who was bidding for government contracts. They wanted to be able to develop very accurate bids, but they wanted to be able to do this quickly. It was important that the bid was accurate because if they bid too much, they wouldn't get the contract, and if they bid too little, they would lose money. And we were able to take a software product line approach to help them in developing process that brought the time length for producing a bid down from months to just a few days. We've been working in the area of adaptive security and privacy, in particular with the cloud and with smart buildings. So we're working with, for example, United Technologies, who own Chubb alarms, Otis elevators, and many other building-related technologies and technology providers, and we've been working with them on how we can change security policies as different assets are in the building, different visitors are in the building, etc. We've been looking at how we can parallelize code and how we can exploit new versions of hardware such as multi-core. So we've been working, for example, with a company called Methodologies, whom most of you probably never heard of, but in actual fact, most of you probably do use their product because they provide processors that are used in virtually all smartphones. So we've been working with them on how we can use multi-core to build smart cameras that a lot of the processing can be done in the camera rather than having the overhead of transferring data back to a centralized location. We've been looking at, particularly with financial services companies, on how their software has changed over time and how we've had architectural drift so that what was once the design is no longer the design of the system and the system has changed. So we've been looking at how the reasons for why that happened and for putting in place mechanisms to control that. So we don't necessarily want to stop it, but we want to know if we're making a change to the architecture and that we have a record of this. We've been looking, particularly with IBM, on performance evaluation in large-scale systems. So, for example, in server farms, and Lero has actually had a successful spin-out company in this area. And my own area, as Stephen mentioned in my bio sketch at the beginning, for many years I was director of the software engineering laboratory at NASA Goddard Space Flight Center. So I've been working in the area of autonomous space systems for the best part of 20 years and also working with the European Space Agency in doing that. So I'd like to give you one example from my experience developing space systems. And as you can imagine, space exploration systems are some of the most expensive software applications ever. And the huge levels of autonomy are involved. And of course, the consequences for failure are great, not just in terms of cost, but also in the disappointment of spending perhaps 20, 25 years in developing a system that then fails. So current ideas are to use swarm technologies. Now, swarm technologies have been used in many other areas, such as drug discovery, where I understand that significant advances have been made. Swarm technology has been used in communication systems, particularly in broadcasting video, video on demand, etc. And of course, it's used a lot in environmental monitoring, and people tend to forget that NASA are concerned as much with the ocean and the Earth as they are with space. And of course, in our own situation here, is to use swarm technologies for exploration. The idea is that you offer a smaller spacecraft and use a coordinated effort between the spacecraft that can better use solar power. It can go to places where large craft could not go. It can do more complex things by having multiple components working together and give greater accuracy and flexibility. But of course, the big thing is that it gives resilience, that one loss does not mean the loss of the entire mission. So I will explain to you now briefly our approach with the autonomous nanotechnology swarm. This is a multi-mission that has a number of subsets. One of the missions, Lara, will go to the lunar surface and explore the surface of Mars. Another, Sara, will go to Saturn's rings. And the more complex, in my mind, and perhaps more interesting, is PAM, which is the Prospecting Asteroid mission. That's to go to the asteroid belt and discover more about the asteroids. And of course, with NASA's goal of putting a human on an asteroid, this will be even more important. So this is the concept mission of PAM. And the idea is to launch a large craft to go to L1, it's the Lagrangian point, the Earth-Moon Lagrangian point, from where a swarm of 1,000 spacecraft would be launched. These will be small, roughly the size and weight of a laptop, although I guess that's getting smaller every year too, but roughly the size and weight of a laptop and pulled by gravitational forces out into the asteroid belt, taking 3-4 years to get there. The idea then is to group together into small subswarms which have a ruler and a messenger and a number of workers. And the workers are all identical except that they carry a slightly different device for collecting data, whether it's an X-ray, camera, etc. And the intent then is to work in this harsh environment for a long period of time, collecting data about asteroids of interest. Now, the problem with this is that it is so far away that the round-trip delay for a signal is approximately 40 minutes. So that means that if one of the devices were to send back a message to Earth saying, we have this problem, even if Earth could solve that problem immediately and give out new instructions, then the time lag would be 40 minutes, and therefore the mission would be lost. So while having multiple devices reduces the likelihood of a single point of failure, we still have to have this adapting out in space by itself. It also has the problem of worrying about solar storms. So the sun is a star, and stars have stardust, and that sounds very romantic, but in actual fact it's space junk. So junk can be ejected by the sun, and solar storms can also provide a risk of damage to the devices because of electrical charges. So in such a situation, these devices will have to put themselves into a sleep mode, and then when the storm has passed, open up again. Luckily, we get about 24 hours notice of a solar storm by watching the solar disk, so this is something we can actually deal with. So the technologies that we've been using in this are fourfold, and of course there'll be many, many more by the time this finally launches. I should emphasize this is a concept mission, and NASA missions are 20-25 years in the planning, so it is likely to change dramatically by the time that it actually comes to fruition. I should say, however, that the first time I described this mission at a space conference, it was the first talk of the conference. It wasn't a keynote or anything. I just happened to be the first speaker. And somebody at the back of the room stood up and said, I'm glad to see we're starting this conference with science fiction. And I should emphasize that this technology does exist. This technology is possible. It just has to get an awful lot better and an awful lot cheaper before the mission will actually launch. But more so, this is going to be used as a test bed, if you like, for understanding more swarm-based exploration in the future. So as I mentioned, we have contributions in 4 areas: formal methods, autonomic computing, software product lines, and automatic code generation. And I'm just going to talk to you briefly about each of these. So we had a project for a while called Formal Approaches to Swarm Technologies, or FAST, and the idea was to see what way could we go about formally specifying these types of missions, because we want to be able to give a broad range of opportunities for change, but we want to be able to constrain the change also so that we don't make silly mistakes and silly choices. So what we did was develop essentially a dashboard of different formal approaches, everything from things like CCS and CSP, which are used primarily for communication and concurrency, through to things like X machines and Z, which are used more for model-based approaches. We also added probabilistic versions, and this was problematic though because we're mostly guessing at the probabilities, and many of the probabilities are very, very small, so when you combine lots of small probabilities, you get really, really tiny probabilities. So this was an interesting exercise and an interesting approach, but it didn't give us something absolutely ready to use. One of my postdocs, Dr. Emil Vassev, has been working on building a formal specification language for these classes of systems. And he has built a highly successful approach called ASSL, Autonomic System Specification Language. And we've been using that in projects with NASA and the European Space Agency, and a European Union FP7 project used it as the basis of a knowledge representation language. And that has turned out to be very, very useful, in particular highly autonomous applications, because it has built-in primitives that are appropriate for this. We've been using the concept of autonomic computing, where we're taking inspiration from the human body or the mammalian body and the autonomic nervous system. It's got two components, fight or flight, which is taking short-term care. So think of, for example, if you touch something hot, your automatic reaction is to pull back your hand. These are the sort of things that the body does naturally. And then we also have the rest and digest component, or the long-term health of the body, and ensuring that it's healthy over periods of time. So we've built up together with my colleague Roy Sterrett at the University of Ulster, we've built the concept of an autonomic environment where we have a number of components. So we have a heartbeat signal that shows that something is alive. We have a pulse beat signal that shows the health of the body, and by encoding the pulse in different ways, we can identify problems or no problems. We can put components into sleep mode when we don't want them to get damaged or we don't want them to interfere with other components. This could be, for example, a damaged device, or it could be during the solar storm that I mentioned. We can have a component reawaken and come back into operation as necessary. And we have developed a mechanism whereby we have what we call an autonomic license, or an Alice signal, a negotiation between multiple components in the swarm. We've also been looking at how we can use feature modeling from software product lines to specify these types of systems. So here you see circled one of the self-protection mechanisms. In this case, is dealing with the solar storm, but we could then reuse the same software in, for example, the exploration of the rings of Saturn, where the issues are not the solar storm anymore, but other problems that we need to protect from. So this self-protection mechanism could be swapped out for something else that has been defined appropriate for dealing with the rings of Saturn. We've been looking at how we can generate code automatically, and our approach is called requirements to design to code. So the idea is that we want to be able to start out with our requirements expressed as various types of scenarios, and these may be written in English, or they may be written using a constrained language, or written using some sort of notation, whether it's UML or whatever. We want to generate code. If we have appropriate models, we will be able to do that code generation. So there are many tools that can take models and generate code from them, and there are existing tools that will extract models from code. There are also laws of concurrency that we can write mathematically that describe the result of putting components working together in concurrent operation. And if we reverse these, we can actually give ourselves a whole round-trip approach to software development and automatic code generation. So we've built some of this. I don't think this is going to be very clear on your screens, but you'll see the different type of shading where we're using some commercially available tools, some tools that have been built specifically for the purpose, and then other tools that are customized to work and develop this approach. The advantage of this method is that we can automate the entire development process, so we can generate code automatically, and we can regenerate code automatically, which is equally important. We have a significant increase in the quality of that code. We're able to do a formal proof about properties of the implementations because we have a mathematical description of how the components interact. We're able to do a formal proof of correctness of the system, and we're able to do a sort of automated what-if analysis because we can see what difference is by changing specific parts of the system or specific decisions. But the important thing is that we have a guaranteed correspondence between our requirements and the actual implementation as code. So we've used this in generating automatic code generation for provably correct systems. We've used it to re-implement after requirements changes. We've used it to exploit reuse across different platforms so that we can write one set of programs but implement it in different types of hardware. And we've been able to reverse engineer some legacy systems to a version that is more mathematically sound. And we've particularly been doing this with satellite operations. And we can use this to document existing systems, such as expert systems, where we didn't know what the rules were, but we're actually able to provide an analysis and a documentation that can be very useful. And then, of course, we can re-implement legacy systems in a new way, in a new implementation that we know how it works. So we've applied this in some agent-based systems. We've applied it in wireless sensor networks. It's been applied to parts of this ANTS mission, which you could consider to be a wireless sensor network on steroids. And we've also used it in a particularly interesting application, which was the verification of the robotic procedures for the Hubble Space Telescope, which, as you know, was originally to be done by a robot, but later was done by astronauts and a robot combination. This is the Hubble. The original idea was that it would be taken down every few years, maintained on the ground, and then relaunched. This didn't turn out to be feasible because the solar panels had to be changed and it no longer fit into the space shuttle. But the idea then was to do a robotic servicing that a large robot arm built in Canada would be brought up and would run for 8 hours. That was the length of its battery, and would have a number of tasks to do. The problem is that these tasks took years to actually determine what they were, and the problem is that the timing constraints for these would not be known until the actual mission was launched. The whole idea was that there would be periods of time when things could not be done because it would not be safe to do so, but these periods of time were not known until the mission would launch, and then this meant that all of the requirements would have to be recalculated within a matter of a few hours. These are the requirements that were originally to be used. You see the first column is a set of timing constraints. Then the next column, the larger column, is the robot arm itself, which moved, and then the two dexterous arms, which were, if you like, the two hands at the end of the arm. Now, this may look a bit like a Word document to you, and there's a good reason for that. It is a Word document. But the big advantage of a Word document is that you can tag it, and you can process it, and you can read it in. So what we were able to do was feed this into our tool, and our tool was then able to generate a formal specification that is equivalent to this. And our approach is called R2D2C, and what you see here is a formal specification written in CSPM, which is a machine-readable form of CSP. And then we were able to execute that in Java, and you'll see that we had a problem. We kept getting this deadlock. It turned out that there was a constraint on the first line of the instructions or the requirements that actually was invalid. Now, that's not to say it would not have been found, but it was very nice to find it with the tool that we use for automatic code generation. So, our next approach was to use this for the larger future NASA missions, and of course some of these have been put on hold and put back for various reasons, mostly financial. But what is important to realize is that just because we have something that's worked out well on paper doesn't mean it's going to necessarily scale up. There are many approaches to software change that we need to understand and we need to approach carefully. We believe that we need this area of evolving critical systems to be able to build a proper environment in which software can be changed. So that software must change. We must allow software to change. Remember, if it didn't change, we'd do it in hardware. There's always going to be a trade-off between the reliability we need in our system, the predictability of how much it will cost, and the fact that we need software evolution. So we believe that there's a need for this evolving critical systems research effort. And we at Lero, along with some of our colleagues and collaborators, are leading that effort. Quote from David Wheeler. David Wheeler was the first person ever to get a PhD in computer science. Not to say that other people didn't get PhDs in computer science areas before that, but they would have been PhDs in mathematics or PhDs in electrical engineering, and so on. David Wheeler was the first person to get a PhD in computer science. You probably don't know his name, but he invented the Wheeler jump, what we now call a subroutine. He said that any problem in computer science can be solved with another layer of indirection, but that will usually create another problem. Thank you very much for your attention, and I appreciate you joining us today.
Thank you, Mike. And let's now move on to the questions and answers. And our first question is, how do you estimate the cost and time needed for a software project, and how do you compare your methodology with the traditional approach?
Well, I don't know that our methodology is terribly different from the traditional approach, just emphasizing the need that we address the idea that software is evolving and that software is critical to an organization. Now, there are lots of different ways for estimating costs, and some of them have been very successful. Some of them have been well documented and used by large organizations. But there's always a certain degree of a guess. If you take something like Kokomo, Barry Beam's approach, which is probably the best that we have, you're looking at making an initial estimate and then tweaking this. But you're tweaking it based on what you know about the organization. You have to know about the organization, you have to know about the system you're building, you have to know about your experience of building other systems like this and how you did it. And in many of these applications, we're talking about systems that have never been built before. So, for example, the ANTS mission is far above and beyond anything that's been built in the past. So how we could actually estimate the cost of that using something like Kokomo isn't going to work. So unfortunately, it's a bit of a guess.
So here's the second question. Does provably correct mean only with respect to requirements or with respect to purpose? How do you confirm that the requirements scenarios comprise a system that will be fit for purpose?
Right. Well, I mean, there are, of course, many different approaches to requirements engineering and a lot of people working in this area. It has been very successful over the years, and we have managed to produce systems that are fit for purpose. But there will always be a certain degree of having to involve end users and understanding what they really want, and getting this right is very, very difficult.
The next question is, code generation relies on specific tools, and there will be no industry standards. How will this be solved, and who verifies the code generators? Is the approach language agnostic, i.e., because there's no industry standard?
Well, yes, our approach, I should have pointed out, is very much domain specific. So we're not suggesting that we can use the one tool in all sorts of different areas. It has its own lingua franca, if you like, and we're looking at particular applications. That's not to say that it can't be changed to work in other application areas and other domains, but it's very much working in a reduced breadth, if you like. We have actually licensed this technology to a company that writes code-generating software. I'm afraid I can't name the company, but they will be embedding this technology in their code generators. I will say that a number of years ago, in a prior position that I had, we were working with a company who were using a popular code generator, and we're finding that it was generating something like 50,000 lines of code that they didn't know what it was doing. And this meant a big worry because, yes, there's no industry standard. The company that were selling this code generating tool did not give access to the internal workings of it. And so one had to wonder why this code was being generated, and if this code was being generated, what other code was being generated that we didn't know about. So it is actually a very good question as who verifies code generators. That is a big problem, I guess.
You mentioned that it's being licensed. Do you know when that's going to be released?
Well, the contract was to be within 4 years of the license agreement being signed, and that was about 2 years ago, so probably in the next couple of years, hopefully.
Now, how important are regression tests for evolving critical systems? Do you think there will ever be a better way to ensure changes don't break other parts of the code base?
Well, I think an approach based on automating the code generation will certainly help to avoid breaking other parts of the code base. It certainly won't guarantee it, but it would certainly be a help. I think regression tests are important because, yes, as we're making changes, we need to make sure that those changes are valid. And so when we're talking about highly autonomous systems, we're talking about a range of possible behaviors that we would allow. So we're not even talking about what specific changes we're going to make. We're going to say what range of changes we would allow. So, yes, this becomes a big issue. Not saying we have it all solved, just believe that there is this research agenda that we need to address.
How do you ensure an autonomic system continues to have adequate dynamic and integrity limits as it changes itself?
I don't think I can say that I have a definitive solution to that. What we do have to be able to do is to determine that it's not going outside the bounds of things that we're allowing to change. So shouldn't be allowing it to make huge changes in one go, but then there is a time constraint that changes have to happen. So we need to build in the ability to do a certain amount of change, but change that we can understand. So that's why I'm saying we need this area of research.
Does your swarm-based system assume radiation-hardened hardware, or is it designed for COTS?
No, it assumes radiation-hardened hardware. And I should point out that I am no expert on the hardware, and there are many other people in NASA working on this. And I'm just addressing the software aspects. There are many more issues that, of course, have to be dealt with by experts.
Here's an interesting question, and there's probably a good foundation for it, and that is most of the proposals being made in this presentation are ideas I've been hearing for the last 30 years. How do we get the state of the practice to advance, given how little progress we have made in recent decades?
That is a good question. I mean, yes, people have been talking about formal methods since the 60s and 70s. People have been talking about software product lines for the last 25, 30 years. You're absolutely correct. I think we need to get people to understand that this issue of criticality and evolution have to be addressed in what we do. Now, we have had success stories. There is, for example, a software product line Hall of Fame where successful approaches to software product lines have been useful in building successful systems. This is a great idea. It's a great way to publicize the success that we've had and things that we've had that have been useful. I myself, 20 years ago, I did a book with a colleague, Jonathan Bowen, on successful applications of formal methods, and this inspired a lot of people to go ahead and use formal approaches that they wouldn't have considered before. But it's getting the good news out there is important.
Earlier in your presentation, you had sort of some rationale in terms of investment reasoning. So a question is, I don't agree with this investment reasoning. I think you should pull that because it's the quality of people that matter. They'll ask the right questions to keep costs down. So what's your reaction to that?
Well, I don't quite understand the question, and the quality of your people is absolutely essential, and that's why we have to have adequate training and adequate education for everybody involved in the process. But I don't quite understand that you should pull that because it's quality people. Well, people are absolutely essential. Yes, I agree. But what we can do is we can augment those people by giving them appropriate tools to build successful systems.
So in a space system, presumably you want a simulation running on the ground to test changes. It's a question. Do you have a formal method for validating the simulation?
No, but that's something we would want to have, ultimately. We do have a formal method that we can use for simulation. I'm not saying that it's absolutely perfect or 100% bare, but certainly it's the start. I mean, it is a research area. We need to get into this.
So I'm just sorting through some more questions here. What kind of code optimization is involved with automatic generation?
Well, our particular approach is more a demo. We're not saying that the tool is anything like we'd like it to be. So we haven't considered code optimization much in doing that. Obviously, you could do that, but then you're trusting that somebody is making the appropriate optimization. Now, of course, lots of work in compiler technology over the last 50 years has produced some excellent optimizations, but there's always the risk if you're giving somebody the opportunity to make optimizations that the optimization could be the wrong one.
A lot of software development now is about selecting, composing, and maybe tweaking existing third-party off-the-shelf systems. How can we evolve our software as these third-party systems change, disappear, or are surpassed by other systems?
Well, I mean, it depends on your approach. Yes, certainly there's a lot of good work out there that we can reuse, and I don't agree with rewriting everything from scratch if we don't need to. But yeah, I mean, this is something we have to work on.
What tools can we use to describe software-based execution environments? For example, you showed us a language tool for space systems. What language or tools have you seen for internet-based applications?
I don't claim to be an expert on this at all, but I mean, certainly it would be important to look at what is needed by the organizations that are looking to change their software in this domain. So I would say I don't have a specific tools or technologies in mind, but certainly these are things that we can investigate.
Here's another question. What about security of the critical system and working towards secure applications from the first? We have seen car hacking situations like Stuxnet. How do you think things will unfold going to the future with the Internet of Things?
Well, absolutely. I think it is absolutely essential. I mean, we've had examples of, vice president's pacemaker being turned off because the danger that somebody could hack into it. So, I mean, yes, I mean, as we have more and more devices connected and as we're trusting more and more devices, certainly the security aspects are becoming a big deal. So I would certainly say that security is a major aspect of this evolving critical systems research agenda.
Now, I'm a big fan of MATLAB.
Mm-hmm.
Sorry. Go ahead.
Sorry, Stephen, go ahead.
Okay, I'm a big fan of MATLAB and the programming modules they give us with simulations and Simulink and Simscape. Do you have a programming IDE favorite, or do you prefer freestyle programming?
Well, I have to admit it's been a long time since I've written a program. I've moved away from that. I do have people in my group who are very big fans of MATLAB, and I would be very happy with that. I wouldn't say that I have a favorite myself. We've identified problems with existing code generators, which is why we took our own approach to code generation that we felt was a useful and valid approach. And now, as I say, there is a code generating manufacturer, a supplier, a vendor, whatever you want to call them, who will be using this technology in their code generator. I'm sorry, I can't tell you who they are.
It's an interesting question. Dr. Hinchey, please address the human side of evolving critical systems, i.e., how can we ensure that people and their cultural practices support the methodology instead of impeding it?
I'm trying to find the question here online because it's a fairly long one. I don't quite understand the issue of quality of people is absolutely essential, but we can give people tools that will make them more productive and more useful. I don't think that answers your question at all. I'm trying to find it here online so I can read it if you can.
And let's see if we can find one more here. You're ending at the end, so end with a little bit of fun note. I think it's Gaelic, right? What does it mean?
Hello, Stephen. I think I've lost you.
Mike, you had this go race or this saying on your last slide. What does it mean?
Oh, the last slide? It says Gurav Mahagas. Thank you. It's Gaelic, so it literally means that there was good in you. But anyway, it means thank you.
Well, I'm afraid we've run out of time today, and so that was our last question. So it ended appropriately, okay. And I'd like to thank Mike Hinchey again for his informative presentation and insightful answers to the many questions. And a special thanks to each of you for taking the time to attend and participate today. Now, this webinar was recorded and will be available online in a few days at learning.acm.org/webinar. And you can find announcements on upcoming webinars and other ACM activities at learning.acm.org and acm.org. Also, please fill out our quick survey where you can suggest feature topics or speakers, which you can see on your screen right now, or click on the survey icon in the menu dock if you don't see it on your screen. Now, on behalf of the ACM, Mike Hinchey and myself, Stephen Ibaraki, thanks again for joining us. And I hope you will join us again in the future. This concludes the webinar.